Here one by one, and show you work, okay? So that you can appreciate what you've done, not only what you first step. You can still show it, you haven't even started, then you will have to come. But when you get here this time to see those repetitions and their moments, you should be able to how this problem can be solved, right? Okay, so we will start from the first bench and we will go in this particular order, okay? Make sure that you can connect your laptop because that was something that you were struggling with yesterday. Okay, it's good. So can you also display the question first so that people know what you're talking about? Morning. Yeah, just for your information, the minimum for the first function is 0, 0, 0, 0. And for the second function, it's set 1, 1. Okay. Can you zoom it a little bit so that everybody can see it? In the tolerances, and iteration I actually kept it little higher because some method actually was going was taking a lot of iterations, especially the steeplest descent and the atom actually took a lot of iterations. Confidence value was the least. So when I ran this, so the minimum was coming here close to 0, right? And iterations was quite less, right? And this is the objective function. 7, right? 7. And then if you just change it to conjugate gradient, so it is so here sorry, Newton was taking less equations, so it is 24. Yeah? So this is the for the function 1 and this is the minimum value. Now for the second method, similarly I have done it for the Newton and the CG. Since it was 2-dimensional, it was easy to plot it now because you can keep a track of how the x0, x1, x2 are evolving. So this one for the Newton, it actually 39 iterations it took, and the minimum came out to be 1, 1. Okay. And then I plotted the path, how the iteration went. So depending upon the starting point, it will change. So if I change the, for example, Here if I change the starting point, so the path to convergence changes. Then the next function was the steepest descent. We just did it for the function 2 because it was easy to plot. Function 1, there are many variables. So this also works, and this actually for the second function it came out like this, and the number of iterations was 5,000. For this one, 0.91 and 0.84 for the second function.
Okay. So you want to get to the one, okay.
Yeah. Steepest descent, and then for the Adam optimizer, we use the same methodology using the momentum term and whatever sir has given.
So you try to do?
Yes, I took a little bit of help, but again I understood.
Yeah.
So this one actually converts nicely, and the number of iterations was this much. So steepest descent, I think conversion never an issue. But the conjugate gradient is Newton gradient. Okay, I will try that. Make it 0.1.
What do you mean now?
0.01.
Yeah, maybe 1.1, 600 traditions or something.
Okay. If there is a chance, it can offshoot.
Yeah, definitely want to display. Definitely want to display.
Yeah.
This time, you can send it around, you can come back.
Sure.
So who wants to go next?
It's running. Sorry, yeah, this is the way. So learning rate, yeah, play.
Regarding 600 accuracy. So conversion. So this is what Adam does because
So make it 60 iterations here and see.
instead of 600,
But 600 it took.
change it to 60 and see.
Acha, will automatically listen. No. Final point is 0.
See it convert?
No.
What do you want?
Sufficient.
So I actually kept it for 6,000, and then in 400 it
Oh,
increased.
okay, there's a, there was a pressure.
Okay.
Okay, good job.
Okay.
Very good. Okay, I'm not going to look at you, yes. Anybody who wants to come over. I'm going to turn around. You have the microphone.
Put it down on the microphone.
What we have done is
I noticed some libraries and from that language
matplotlib for plots, and that the last library is for to get the plot in a better way. And so what we have done is
Anybody has any question, then you should ask the speaker, because the last talk you didn't say anything.
and
Yeah.
and I have mentioned I have used the optimizer class, and I have defined those two functions that was given in the assignment, and then I have calculated the gradient. Okay, so I have used two methods. This is for the first one. So here I have used analytical differentiation for the gradient calculation, and in the next part I have calculated this gradient part using numerical method, finite difference method. Actually, it is I have specially used central one. So this is the gradient that I have defined, and this is the Hessian for the first function, and this is the Hessian for the second function. And now I have defined just the methods that I'm going to take. The maximum iteration value that already sir had told, that let's fix a maximum iteration value so that it doesn't overshoot. So I have for each and every method I have set a maximum iteration limit and a tolerance limit also. And then okay, so this is the Newton's method. This is the steepest descent method, conjugated gradient. These are the methods that I have just defined, and the adder method. The output.
So did you write the codes?
Yes, sir. I have used some of it from my previous lectures that I have followed from your SEG course,
Yeah.
and they have helped me also. And one of my friend, he's from computer science, so he has also helped me in building this. So the output that I am getting is okay. So here is all of the summary that I am getting, like for the function 2. Okay, this is a function 2. Okay, so this is for function 1. Okay, so this I have taken different this as my initial point. So from initial point I am trying to solve. So for this is for, I guess, yes, this is for Newton method. I have taken different starting points to converge at the minima. Okay, so here it is showing the final value. It is or almost equal to 0. The final point. Okay, so first iteration I have taken a point farther from the from the minima point, so it is showing the final point. But in the next iteration, the next starting point, I'm getting final point is 0. So I guess the for first function the minimum value is 0 0 0 0. Okay, so these are the results that I am getting. I have just used the different methods that was mentioned in the assignment. So, and this is the graph with the change of iteration, how the functional value, it is in log scale, so how the functional value is changing using different optimization methods. And here for the and the same thing. Okay, so one thing is for the first function, it is a 4D function. It is a bit tricky to, we can plot it in a 3D or in a 2D. So that I have also plotted in a
So
different
don't hurry up. Just show it and discuss what you have in that figure.
So
in that figure, what you
in
have.
the figure that in the first starting point, the as you can see that how the functional value as we start from a different. So as we have seen that in the second starting point, it has come close to 0 in in two iterations. But in case of when we're starting from away point, then it is taking too much iterations. So the functional value is changing in a in the blue, not in the blue, oh, in the green and the red pattern, that is showing that how we are taking different starting points, how the how the functional values are changing with the change of iterations, with the number of iterations it is as I'm
And this is
increasing.
which method?
Sir, the first one is for Newton's method.
Okay.
Second one is for steepest descent. It is for the first function only.
Yeah.
And conjugate gradient and Adam method is the last one. So, and for the second function also, I have done the same thing, the same process that I have done, and I am getting the 0. Okay, so here we can plot it in a 2D because it is in function of x and y. So I can show that I am taking different starting points, like in the white line in the first. I'm just showing that in the Newton method, Rosenbrock function. So first point I'm taking from there, like in the white line, we can see, and that the star point is the global minima, and the yellow line I'm starting with some random point, and then how I'm getting the path is also shown, how the optimization path it is taking. So that I have already defined in the definition part of this optimization process, and this is how it is changing with. So this is the same graph for as we have shown in the previous section, how with the change of different methods, how the error, like how the functional value is changing with the change of iteration values. Okay, so this is the comparison that for the two functions, for the first function and the second function, and this is what I have just written, what it is, how it is doing, like in the comparison between four different methods. Okay, so this was the actual assignment, and so I have done a little bit more. So this is next time in the next part that I have used optimize a different library also, scipy dot optimize to get the optimization function. Okay, so for the first function I have tried to just show how, for the first function we haven't seen that graph part, like how the function is there in the graph. So okay. Okay, so this is, I've taken a one component, let's say W component 0, and for the different three values, I'm taking different starting points, like the red dot, the blue dot, yellow, and the green dot, and I'm coming back to the global minima point, and the optimization path is also shown here. Okay, so this is just for the first function, and here is the comparison that I've done, like how it is like taking how many iterations, that as we can see that in the Newton method is only taking 2 iterations to reach to the global minima, and steepest descent is taking 98, 47. Adam method is taking too much like iterations, and after that this is the final value error and the average solution errors that I have also plotted. And okay, so for the function visualization, I have done a little bit more for the first function visualization only. Okay, no, this is for the second function. Okay, so for the second function, here what I have done is, for the first time I have calculated the gradients using the normal analytical differentiation method, but here the differentiation methods for the gradient calculation I have taken numerical methods, like not steepest gradient, this is a finite difference method, especially the central propagation. So here I'm getting a plot like this. Okay, so these are the and I have shown how it is changing, like the thing that is analytically how much it is giving us, and the numerical part. So numerical part is giving a pretty good result as compared to the analytical part. So this is just the analytical, and this is the comparison of how the analytical is doing and how. Okay, so for the Newton. Okay, so this is the Newton analytical part. These are pretty easy. So here, Newton analytical, I have shown that the previous one, and this is how I have done it in a numerical way.
Okay.
So this is the comparison of both of them. And this first function I have also done. Okay, this is for the first function. This is how I'm getting analytically, analytically solving the gradients, and I'm getting this result. This is the Adam and the conjugate gradient. Here Newton convergence and steepest descent. So there we were getting a flat line close to zero, but here as we are taking it in a analytical way, so it is taking a initial point, then forward propagating, then backward propagating, taking 2 points. As I have used the central one, so it is taking a 1 point back, 1 point forward. So I'm getting the result like this. And okay, so this is the plot. This is the comparison, like how many iterations it's taking for the first function. It's almost the same I'm getting. These are the summary of the first function, that how Adam method is better, or how steepest descent or Newton method is better. That is all has been jotted down here. Okay. So okay. So that's it from my part.
Okay. Any questions? No question? Then thank you. Good job, okay, guys.
A very good morning to everybody. So, like, I'm very new to this, and also we are working in a group. Like, we were discussing how to do it. So, we are behind how it works at the back end. Like, we tried not to use the libraries and go with what is the basic thing. So, just to show, we have worked like only with the second equation. Like, that was pretty simple. That's why just we wanted to first go for the simpler one. So, first, when I show like what actually in steepest descent happens is what we want to achieve actually. Like, suppose I have some x and y. So basically, I just store that into a single matrix like x1, x0, and x1. So when I update my x value, so how and what it happens basically. So when I get a new x, so it should be somewhat like the previous x minus the learning rate or the step size basically which I am using, and the first derivative of the x, the function basically, the objective function. So this is what I use for the steepest descent. So when I show you in the code, so this one will be the steepest descent. Like in this, a and b are the parameters. Like this is the function basically which was written like that. So this is df by dx, df by dx, and df by dy. So basically we are just doing the differentiation with respect to x and y. So we try to write it in a way, and then this is for the first one. And when we go for the Newton, so these are just like I have gone for the basic function, Rosen function, then the gradients, and then the partial derivatives, basically the Hessian function.
Good.
So when we first go for the gradient descent, the equation which I've showed, I've just skipped it here. So what we do over here is, if you can see over here, so g I give to the gradient, so basically the first derivative, and then when we go for the new x, like which is updating with every iteration. So basically I run here to 20,000 iterations, suppose. So when I update it, it is something like x minus the learning rate, the step size which it is taking into the gradient. So then we check for the norm. Second, so np.lineelect.norm uses the second norm, L2 norm basically. And then we check, we have given some tolerance. Okay, so we have tolerance like if it is less than this, then you break, like the loop will break, and that will be our final solution. So that is how it works. And just when we go for the Newton, the other thing is just we are using the Hessian matrix, that is the double derivative, to solve with the partial derivative. Like that is f dash by fx. Like I can show you the equation. Okay, so this is how we update in the Newton's method. Then in the conjugate, this is what I have shown. Like for the conjugate gradient, like I was trying to, but I couldn't, so I used a library. So here I use scipy.optimize, and from there we import minimize, and in that we use this method. And Jacobian matrix over here we give the first order derivative, the gradient we have used, and we have given the tolerance at 10 to power minus 8. So when we run it, so we just also print the number of iterations every method is using. So this is how we go for it. So in this cross gradient, conjugate gradient, it actually updates the learning rate every iteration. And then for the Adam, like we have just tried. So basically, I could just go through some internet sources and try to find the formulas basically. So we're behind those, like more than the libraries. So here it is somewhat complex. So I've just tried. I've taken some help from other sources as well. So I've tried to code it and run for the simpler equation only, like the second one. So when I just run my code completely, so this is the function for the second equation. So I give learning rate beta 1, beta 2, and epsilon. And when I just run it for everything here, so this is what we get. So basically the result was somewhat, it should have converged to 1, 1. So when we see for the Newton descent, it only took 7 iterations to come from 1, 1. So that also depends on what are the initials that we are taking. So basically like minus 1.5 and 2 we had taken for x and y. So basically we could see like Newton descent, it worked very fast. It came in just 7 iterations. Then steepest descent, it took around 15,000 iterations. Maybe if we give it more close x and y, it will converge early. And then we see for conjugate, so we get in 30 iterations. And for Adam, like but also one thing is to like what we can notice is gradient descent and like basically the steepest descent and Adam could not actually converge to 1, 1 for what parameters we had used.
Okay.
So this is what we tried to do in one day.
Okay, so you need to also run this first function. Yeah, you guys, since you already have the code, in fact, that's actually a simpler problem than this.
Okay.
So you should try to do that one as well.
Yeah. Okay.
Good, very good. I'm glad you wrote your own code. Yeah.
A very good morning to all. So this is the all the libraries, and I have used the functions for the second one, and this is the steepest descent one. I use the functions to use the steepest descent. So this is the function, and then take the gradient of f. So what is required? So the starting point and the learning rate, which is 0.001, and the tolerance is 10 to the power 6, and I use the maximum iteration of 10,000. And this is the whole procedure, as we all know that. I'm not going through this. And this is the same functions I have used for the Newton's method. So this is the whole, whatever the algorithm is used as a Newton's method, it's defined in the functions, and it is for the Adam optimizer. And this is the same functions I have created for the plotting it. And this is the plots we are getting with all the paths as follows for the second function. And here I use the starting point as a minus 1.5 and plus 1.5. And this is for the second starting point. So this is showing the all the paths that is follows for the different methods. and this is for the first function. So the same procedure I followed, but here I didn't use the grad functions to create the gradient, but rather than using the in general method, and it is the Hessian matrix, and this is just all the starting point, initial points, and then I use the path functions, so where I store the paths of the different methods. The same procedure like the steepest descent functions, and then the Newton's method, and here I got the result. That is the convergence of the functions for the different method like the steepest descent, Newton, and the Adam optimizer. And this is the this is the initial starting point, and here is the final point we are getting. And for this first function, we are getting the 0 point, and it is the case for the Newtons. And this is the for the Adam.
So how many iterations they
So
took?
for the Adam, it reaches to the last iteration like 10,000.
Okay. Okay. Okay, any question for this group? Okay, good job. Okay.
Thank you, sir.
Anybody else coming? Nobody from the back?
So we have inputted the function that was given in f and took the gradient of that function.
So microphone, can you use that one?
We have used a function that what we have done is we have used a function f and gradient f that was given, and then we put the Adam optimizer, this code, and then code called Newton method, then steepest descent, and then the conjugate gradient, and then we have plotted one by one in the same graph, which is this one.
Okay.
Yeah.
So did they all converge to the true solution?
No, sir. Like the Adam one is a bit more converged than the Newton method.
So what was the value at the time of convergence? What is the function value? Did
So,
you print it or
no,
not?
sir. That I have not printed. I have just plotted it.
What about the XY value there's? What about the XY values for those?
That I have put it in a range that goes around 2000 steps.
No, I think you have plotted it, but you didn't print the last coordinate. The last value of the coordinate. Point nine. Okay. Okay. Continue.
We have put it the functions directly using some libraries, and all have been plotted nicely.
So you didn't do the first function? The function of 4 variables.
We have taken the second function, which is of x and y.
Okay. Okay. Okay, you should try to finish the first one also. Okay? Good. You were a part of that group? Anybody else there? Or is that the last group? Is this the last group or is there somebody else who wants to show? Okay.
So we have first we have tried with the analytical gradient and Bayesian function, and we have first tried to do the second function because
And did you use optimization libraries or?
yes.
Okay.
So we have taken random points and see how it converges. So the initial point is 0 and 0. For 0, 0.
And what are the methods? Do I mention the methods for these?
This one is only for Newton. So Newton, you see the curve like this, and then we have assembled all the methods with different initial points, and we have plotted the contours to see how different algorithms converges from the same initial point. So these are the minimums. These are the minimums, and these are the number of steps. So we see in each of the results, each performs better. It takes less number of steps to converge to the minimum. Followed by adder. And for the first function, we also see the same pattern following C because the Newton performs better.
So they always found the minimum value, or some of them actually diverged or not?
Some of them diverged.
Okay.
With different initial points, you see that for Z and W, it's not getting the 0, 0.
Yeah.
So for W, it's not able to. Don't know like why it's not
Okay. Okay. Good. Any questions for him, for this group? No. Okay. Okay. Next group. Is this last group or what? Okay. All right. So some of you actually didn't turn up, so that means you probably haven't done it. So what you can do is you can get the answer. I can send you what I have, and then you can play with it and teach yourselves. What I got is no different from what you saw, what these people have done. But my question to all of you is that let's say that you have these codes, and now you have some geophysical data that you want to invert, right? What will it take? What else? Okay, what else? So objective function takes the place of. Good. And you evaluate only after you have solved the problem, right? What else you need?
Solution, but anything else you need to know these codes?
Constraints. Constraints. Constraints.
Constraints, yeah, no, but this is not constraint. Anything else?
No, this is message you already have.
You see the point?
Yeah, somebody already said that. What were labels to these it's to these optimization routines? Come on.
Learning it steps.
Yeah.
Shift direction. Direction.
What did I do in direction?
Good. You have to be able to gradient also, right? So solve the problem will give you the function, then you have to be able to compute its gradient also, right? And how would you compute the gradient? You cannot always compute it by finite differences, right? So then you have to see if you can come up with a clever algorithm for doing that. Okay? So you already have the codes, you can go home and you can run it and apply it on some geophysical problems. Okay? Okay, that's good.
Now we move on to a new topic.
Optimization. So I hope you are quite comfortable with local optimization methods. What I wanted to basically tell you is that what you've done in the class is something that you're going to be using all your life, okay? And to solve any problem that you want to work on, in a parameter estimation problem, you'll always need to solve an optimization problem. And gradient methods, gradient-based methods, and local optimization methods are the state of the art. Almost every application that you find uses some variant of local optimization methods. So we are going step by step. First, we talked about a linear approach And linear approach, we had used basically least squares, which was a simple single step method, right? And then we started with nonlinear, but then we use local optimization. And local optimization methods basically typically make use of some gradient and perhaps Hessian in case of Newton method. So sometimes these methods are also called calculus based, okay? Because it's basically using calculus, talking about derivatives, right? The limitation of these local optimization methods is that they're very sensitive to the choice of your starting model, right? And you already saw that when you did the exercise. And you will see it even more when you apply it on some real problem with a lot of parameters. So you have done it for 2-parameter case and 4-parameter case, but any other problem that you want to try will have a lot more parameters, right? Say, for example, if you're doing resistivity inversion, right? So how many parameters are there? Typically, how many parameters you would solve for? You have an apparent resistivity curve, right? And you're trying to build a one-dimensional velocity model. How many parameters you can have? So typically you do it as a function of depth, right? And as a function, so you put in a bunch of layers. So if you have, say, 5 layers, then you have 5 conductivity and 5 thicknesses, so that makes it 10. If you want to make it more complicated, then more layers, then you have number of layers times the number of layer times your number of layer times thicknesses and number of layer times resistivity, right? So basically you have 2 NL parameters, right? What if you have a laterally varying velocity model? You don't assume 1D, okay? But it's a laterally varying medium. Then you have to represent this in terms of grids, right? Then the number of parameters should be same as the number of grids. So you can easily have like 100 by 100 in 2D, right? So that's how many? 10,000, right? And if you did it in 3D, let's say that I have 100 by 100 by 100. So you can see there's a lot of parameters. So you'll have to solve your forward problem. And in this case, you have to use finite differences. Then you have to evaluate the objective function and also be able to compute its gradient. And that gradient vector will have how many elements in that vector? This is a vector, right? So what is the dimension of this vector for this problem, for 2D problems? You just, So same as the number of parameters, right? Because with respect to each parameter, you have to compute its gradient, okay? And so you can see that this has the same dimension, like 100 by 100, that in 3D it's going to be 100 by 100 by 100. So it's going to be a big job, but the same code is going to work, okay? because in your code you didn't basically force your dimension of the function, right? So that's a very important lesson that you have. In case you didn't do this before, this is something that you're going to be using a lot. Okay, so I talked a lot about the gradient methods, but then there is another class of methods called global optimization. So these are all local optimization, and then this is called global optimization methods. Now, before we talk about global optimization methods, no matter what method you use, you always have to start from somewhere, right? And then what is the next step? Next step is to find a direction, right? And we very cleverly what is the other choice? Don't use any direction, but look everywhere, right? So what it means is that if I have 4 parameters, I can basically change one at a time and then solve this problem. What if I just change the model at random? So changing the model at random can either give you a good model or a bad model, right? And that is the idea we're going to see here. So there are these methods. One is the grid search or enumeration, which means exhaustive search. And then we have this method called Monte Carlo method, which is random search. Then we have simulated annealing, genetic algorithm, and there's a whole bunch of others, PSO and all that. I don't have time to go over all of that. But the most important of these would be probably simulated annealing and some genetic algorithm. Okay? Here, the philosophy is quite a bit different from what you just did with gradient descent methods, and that's where you need to pay attention to. So let's first look at this grid search method. Okay. So what do we do in grid search? Here, let's look at a simple inverse problem. This is a nonlinear problem because this data is given by a nonlinear function of the model parameters M1 and M2. Okay? So I have 2 parameters, M1 and M2. So this is another function. So this grid search method you can also try
on the 2 functions that I gave you, okay? And you very quickly learn
that it's impossible to do grid search on maybe more than 5 or 10 parameters. Okay, just you will run out of computer budget. Okay, so this is omega 0 is a constant, and this is a sine curve plus some shift, right? And then the true solution here is M1 equals 1.21 and M2 equals 1.54, okay? And let's say that you have generated this data and added some noise to it, okay? And this is your true solution of the function. So here, what you can do is you have 2 parameters, like you have M1 and you have M2, right? So what if I put a grid here? So and I choose like maybe 100 values of M1 and 100 values of M2 here, right? So how many models are possible? Here, 10,000, right? So you have 10,000 models. So you can compute your function value at each one of these points and then find the minimum, right? Say, for example, Rosenberg function that you actually plotted very nicely in 2D. It already has all the function values. If you simply ask your function, there is a call to find the minimum of that, it can look and then find the minimum value. Okay, so this would be called grid search. So here you can choose the grid with the smallest value, and you can say that I found my answer. Well, you might say this is a stupid method, right? But for some problems, you can do that. But there is even for 2 or 3 dimensional problem, this can be very, very expensive if you have a lot of grid, because the resolution of your answer depends on your grid size, right? So what do we do in that case? So here is the function, plot of the function. So you can see this has got multiple minima and maxima, right? So you can actually search and then find the minimum. So let's say that I was able to find this minimum here, which is somewhere in here. Now if you choose very coarse grid, you can do this very quickly, right? So one of the things you can do is, after you have located roughly where the global minimum is using those large grids, you can say that now I will actually make my search window smaller, okay? And I would actually focus in this particular box, right? And here I can make finer grids, and then you can reduce it further if you like, and that way it can be computationally efficient, okay? Now you can do the same thing for a large dimensional problem, okay? So here all that you need is to evaluate the function. No need for gradient or Hessian, right? Yeah. Okay. But basically, grading means it is giving you the points, and it will give you where that coordinate is. Okay. Now you can try this grid search on your both 2D and 4D functions and see how long it takes to find the minimum. Okay. So then came this method called Monte Carlo method. Since I cannot do an exhaustive search, what if I just perturb the parameters at random and hope that at some point it will land into the minimum, right? So in Monte Carlo, the strategy is to compute the error at randomly generated points in model space. So in the entire model space, you can take random walk and can say, this is the next one, and then at random, so you call a random number generator, from a random number generator, you call a random number, and then you can apply perturbations to the current model, and then you have a new model, and then you compute its error value, and if it's not good, then you can just throw it away, or you can just take a step from there onwards, okay? So when you do this, you choose the point with the smallest error as the estimate of the solution. Now this may or may not work depending on how much patience you have, okay? It may even take longer than grid search, depends on the problem, right? But there is no restrictions on the choice of the grid spacing. You can have any small random perturbations, okay? And this is basically continuous, almost continuous. So that's one advantage you have, but there's no guarantee that you'll find the solution. Okay, so here in this Monte Carlo search, we started from here and then it went around and then finally it did find it, but there's no guarantee. Okay, so here it's showing you the error value, how it reduces, and then how the true value of the M1 and M2 are arrived at as different iterations. Okay. If you go to a higher dimensional problem, this is a lot more difficult problem, and in that case, you may not have a very easy convergence. Okay. So, what are the advantages of Monte Carlo over grid search? It does not require any decision on the grid spacing, grid size. Okay. And model space is interrogated uniformly, so process can be stopped when an acceptable error is encountered. Whereas in the grid search, you have to basically evaluate at all points. Okay. And this process is open-ended, and you can continue as long as you desire, right? So, what are the disadvantages? Like I said before, this may actually take more time to generate a point in model space that is acceptable, and it results a different solution every time, because you're starting at random and you're taking the random walk, and then each time it basically takes different path, right? So it can give you different solutions, and you may have really bad luck and it may not converge. Okay? If the seed is the same, then it will give the same path, right? But that is not the idea of random walks, right? Okay? So what can we do that is better? Well, that's where we talk about a method called simulated annealing. The simulated annealing is actually a very useful method, in my opinion, and this was first applied in an optimization problem of circuit design by a few scientists from IBM. That was in the early 90s, and right after that, I published a paper, seismic waveform inversion using simulated annealing in 1991, and Dan Rothman from Stanford actually applied this to residual statics problem. And when we published this paper back in, I remember in 1990, I was presenting this paper. Probably some of you were not even born. I was presenting this paper at the SCG conferences. It was a jam-packed hall because it was new and everybody was excited to hear about this. But after the talk, people say, yeah, it's a good idea. Only you are at a university, so you can try it. It'll never work for industry purposes. But, 20 years later, almost every company is using this. So you just have to wait for the computers to get fast enough so that, more compute-intensive methods can be made practical. So since then, I've done quite a bit of research on global optimization methods. So what is simulated annealing? Before we talk about that, let's just refresh our memory. Monte Carlo method is completely undirected, right? It just takes a random walk. And Newton's method is completely directed. You're restricting your search in the direction determined by the Hessian and the gradient. So can we have something in between? Okay? So can we have some kind of direction built into Monte Carlo method? And that is the main idea. So this is slow but foolproof. This is fast, but we know that it can fail and can fall into local minimum. So Monte Carlo method is actually a global optimization method. So we just can keep on searching, right? But this is very, very slow, and this is, as you saw, it's quite fast, right? So what is the compromise? Can we have something that is partially directed random search? Okay? There's some sense of directivity built into the random search approaches. So here, let's say that this is my contour of the objective function, and this is my starting model, MP. Then if we then we want to basically take some random walks with some directivity. So what is simulated annealing? Now this basic idea of simulating annealing comes from statistical mechanics, okay? Now, which involves analysis of the properties of a large number of atoms in samples of liquid or solids. So there is an analogy between the model parameters of an optimization problem and particles in an idealized physical system. So by that, what I mean is that if you have a solid which you melt into a liquid, then all the atoms are in a very high energy state, okay? And then what you do is you start to slowly cool it, right? And if you cool it slow enough, then it will form crystals. But if you cool it very, very fast, it will basically form glass. So forming the crystal by slow cooling basically means it will find the global minimum energy state. And if you cool it really fast, it gets stuck in a local minimum, and that gives you the glass. So this energy in simulated in annealing, this is the physical annealing process. Energy in that annealing process is the equivalent of your objective function, right? And what dictates the energy? It dictates, the energy is dictated by the configuration of how the atoms are arranged, right? So this will be same as our model parameters. How the model parameters are arranged means what kind of values they take to come to this. Based on that, we calculate the energy, right? But there is another factor which you don't have, is temperature, right? So this takes the help of temperature to determine and to bring it to the global minimum energy state, okay? Any question on this? This may seem like a completely foreign concept when it comes to global optimization, but this is what is basically the idea behind simulated annealing, okay? So let me, so in the terminology of stochastic processes, and I'm actually skipping all the details of the theory. If you're interested, you can look at my book. And in the book, I give all the derivations and all the math behind it. So this is based on something called a stochastic process. And each configuration of particle is referred to as a state, okay? And at each temperature, the solid is allowed to reach thermal equilibrium where the probability of being in a state I with energy EI is given by a particular probability distribution function. It's called Boltzmann distribution. So this Boltzmann distribution is actually this distribution. Okay, now I want you to pay attention to this because some people were already lost. So this is the probability of being in a state with an energy EI, okay? And this EI, you can also think about this. What is the probability of being in a particular, with a particular value of the objective function, right? So now we are doing it in a probabilistic manner, okay? So when you take random walks, what is the probability that you'll be in a that it will have a particular objective function value. It turns out that this is dictated by something called Boltzmann distribution, and this EI is the objective or the energy function. This K is the Boltzmann constant, and there is this parameter called T, which is the temperature. Okay? So we can set K equals 1 for our problem. But what is T, right? So this is just a control parameter for our problem. But how does it change things? So let's look at this. This is annealing of metals. At high temperature, atoms are randomly moving. As temperature decreases, atoms slowly find themselves in a minimum energy configuration, an orderly arrangement of then that results in an orderly arrangement of a crystal. Okay, so again, this is what I already mentioned. We have high temperature atoms randomly moving about due to thermal motions. As temperature decreases, atoms slowly find themselves in a minimum energy configuration to crystal. So I use this term loosely, like slowly cooling, right? What is meant by that? So you have to start at a high temperature and then let it cool, right? So you have to have something called a cooling schedule. And depending on the cooling schedule, it can either get stuck in a local minimum or a global minimum. Okay. So let's now come back to our problem of function optimization. Okay. So here is a function of two variables, x and y, and I define error as 1 minus this. Okay. So what does that function look like? Here I take this function. Remember, I have this, so I can now compute my probability e to the power minus e divided by some parameter t, right? And then what I would do is I would look at this probability, okay, as a function of temperature. And if I show that, what you see here is this is the actual function, and these are the probability plots. So this is your x, and that's your y. And these are for t equals 10, t equals 1, t equals 0.1, and t equals 0.01. Well, first of all, you notice that this function has multiple minima and maxima. Okay, this is a very complicated function. Now, when you actually turn this into a probability, e to the power e by t, and look at it, what are you noticing? Anybody wants to comment?
When it's at a high temperature, looks like a flat surface, right?
It's almost like a white distribution. And when you start to change the temperature to lower and lower value, some structure starts to show up. And what you see is at a very low temperature, this is the most probable solution. So this temperature,
What it is doing is it's like a tuning parameter that is changing the shape of your objective function. Okay? From a very complex looking to something that at a low temperature it gives you a solution which is highly probable, and that is the global minimum.
So what is temperature in this function?
In this function, this is just a scale factor.
That's it.
Okay?
Just scale factor. Yes, please.
Again, the probability is proportional to
Can you take the microphone because I can't hear you?
let me speak louder. So, like, you have taken the probability as is proportional to the negative exponential of energy with respect to the time scale. Like, whether it is respect, like we are taking because we are decaying from, like we are reducing the temperature in order to have the minimum energy. Like, if we apply that to some other problem, like it's to what extent we can use that probability, like whether it's only exponential or we can have any other probability function. Like on what basis we have to decide like that probability maybe is proportional to some.
So on what basis we came up with this probability? So this actually, the idea came from statistical physics, okay, where they were looking at the problem that I just talked to you. So essentially, they were solving an optimization problem, and there is a physics behind why they chose this. Okay. Now, whether this is the optimal choice or not, that I can prove. Okay, but I don't have time for this. So basically, but that's a very good question, because I had the same question when I started to hear about this. You have to use something called a Markov model, okay? And then you can show that the stationary distribution of the Markov chain is the Boltzmann distribution, okay? Okay? So, thank you for asking. But the main thing that I want you to notice here is that as a function of temperature, the shape of the probability function is changing, right? However, I have cheated here. I said that I have all the function values available. That's how I could generate the plot, right? Because if you want to calculate the probability, you have to have this, and then you have to sum over all possible model parameters, right? So, we don't want to do an exhaustive grid search, right? So simulated annealing is the method that actually, or Monte Carlo Markov chain is the original idea. It is the method that tells you how to attain or how to arrive at this distribution without exhaustive searching, okay? So then, like I said, I cannot give you the theory, so I need to just show you the algorithm as to how it works. So coming back to this loss function that we're looking at, the error function, this is the high, this is the medium, this is the low energy or error. See, now another name I got for objective function, right? Which is energy. So we had objective function, we had loss function, we have cost function. Why is it called cost function?
It's actually,
Of course, it could be, but it came from a problem called traveling salesman problem. So, you know what a traveling salesman problem is? A salesman needs to visit multiple cities and come back to the original city where he started his journey, he or she. How can he do that at minimum cost? That is the optimization problem. So in that case, the cost is minimized. And that is how the name cost function came in. Just like from simulated annealing, the energy function name came in. And this loss function, this term came from the machine learning community, because what they see the residual between the prediction and the observation is called the loss, which is backpropagated. which I think Somen will talk about first. This, I think, is it tomorrow or this afternoon? This afternoon, okay? Okay, so now what you need to do first is to think about a probability, okay? And that probability basically tells you how you can move from some m prior to m star, okay? And this controls where you want, this could be a Gaussian with m star as the mean, or mp as the mean, with some variance. In this case, you have this, okay? And this is called a proposal distribution. Okay? And this proposal distribution is quite important because if your proposal distribution is really broad, then it may not be very efficient. And also, if it's very tight, then you're not searching enough. So again, this is something that you have to try. This is the proposal distribution. So typically what we do is we assign it to be a Gaussian around the current model. Okay? And then you draw a sample at random. Let's say that this is what I got, okay? After drawing it at random. So then this could be a high value of error or low value of error. Then how do I decide what to do, right? Because this is not a gradient method. So you have to make a choice whether or not you want to accept this new trial model. This is a trial model, okay? No, we don't know that yet. It's just a new model that you're trying without using gradient, okay?
Is the trial. So we need to go from NP to star.
Then you have to decide. So there are two steps here. One is a model generation, and the other is acceptance or rejection. And how do I do that? Well, if the error is smaller, then of course you accept it, okay? However, if the error is larger, then you toss a coin, for example, biased coin, and based on that you decide whether you want to accept it or not. So literally you don't actually toss a coin, but you decide, you define this probability. Okay, so this probability gives you this is your delta E, which is old error minus new error, divided by this temperature T. So if this temperature T is very large, then you'll be accepting whatever model comes out from your generation probability, right? And if the temperature is low, then there is a probability that you'll be accepting a better model and rejecting the bad ones. So the main difference here between a deterministic approach and this is that accepting or the decision to accept or reject is probabilistic, okay? So, and that depends on this temperature T. So how does it help? Where it helps is to getting out of local minimum, okay? So if you have a function looking like this, and if you're starting from here, gradient descent method goes like this, right? So let's say that you are here, and then you take a random walk, and that takes you at this point, which has a higher value. It's possible that it will accept this with some finite probability, right? And then it will go in this direction and come here. It's also possible that it may actually go back somewhere else, but then it can come back and finally, hopefully, you will reach there. Okay? And this step is crucial, and this is the most important part of this algorithm, that it gets you out of a local minimum. Doesn't matter where you started. Now I have to qualify this statement. This will work if you run it sufficient number of iteration, and it also depends on the cooling schedule. Okay? And cooling schedule and starting model again. The way we choose the starting model is we use a, well, you can choose a starting model from your prior, whatever knowledge you have. So you have certain range of model values. Okay, you pick that one from random or using some probability, and then you look at your then you do a random walk, and then decide you want to accept or reject the model based on this, and this is called Metropolis criteria. There is a famous paper, 1953 paper by Metropolis, Rosenblatt, and a few others, where they actually talked about this method, and this was basically, they proposed it as a sampling method, and then this was actually turned into an optimization method using simulated annealing. So there are two steps. Unlike the other methods that you have done, you just compute the gradient and the Hessian, and whatever comes, you accept it, right? I'm hoping that it will go downhill. But here, you don't use the gradient or Hessian information. You just take a random walk. But then you decide whether you want to accept that model or not. And that decision is made probabilistically. Okay? And that is the main idea. So this is something like, this is exactly what I was telling you earlier. If the t value is very large, so it's almost like this function argument goes to 0, right? And you have probability of 1 of accepting any random model. Okay? So initially you do random search, and then slowly you start to focus onto the global minimum. And this actually helps because we don't have a good starting model, right? In that case, this really helps. And small t values, it goes to 0. That means you will not be accepting a lot of random walks. Okay? And so going from t high to t low, and this basically is called a schedule. So typically we use either a linear decay or sometimes we use an exponential decay. Okay? And in intermediate t, most iterations decrease the error but occasionally allow an m star that increases it. So once in a while, you'll see in the initial iterations, it actually does accept a bad model. Okay? So this is the large T. It goes in all direction. A small t basically accepts almost anything that comes. And so the strategy is to start off with large T, which is equivalent of Monte Carlo, and then slowly decrease T. So this is directed. So it's not quite Newton's method, but because we're not using gradient information, you could if you like, but you don't have to. That is the main idea here. And then hopefully after a large number of iterations, it'll converge. So there are many different variants of simulated annealing that has been proposed. Like we have one called Metropolis algorithm, another is called heat bath, and there's very fast simulated annealing. So let me just talk about these three, and others are not that important. Well, this one is, but it's very special purpose. So what is done in Metropolis algorithm, which is same as what I described, you have a starting model M naught, and you have the energy E M naught. You have a temperature, then you have a new model M1. You calculate delta E, evaluate this probability, and if the delta E is less than or equal to 0, you pick this, or you pick this. Okay? This is exactly the same as what I have been talking about earlier. So if you look at it in a cartoon form, so I have two parameters, for example, and I have discretized it. Okay? So let's say that, no, not two parameters, so I have discretized it. So then what I have, no, I have more than 2 parameters, 8 parameters, okay? This is 1, this is 2, this is 3, this is 4. And these are different discrete values. So let's say that this is my starting model, okay? And then I can perturb one parameter, or I can perturb all the parameters to get to a new model. And this is my new model. And now we evaluate the loss function, and using that acceptance criteria, we decide whether we want to keep this. Okay? Now there is another version, it's called heat bath algorithm. And the way heat bath algorithm works is that you have, let's say that I have 8 parameters, and these are possible values. So it keeps every parameter fixed except for one. Okay? And it can do a grid search for one parameter because that's easier, right? And then it can actually evaluate the marginal probability. By that, what I mean is it will actually evaluate this function e to the power minus e, and this will basically simply, in this case, this will be M2, but all other M's are fixed, okay? M1, 3, and everything is fixed. And here also I have a temperature T. So now this is called a marginal probability because I'm keeping everything fixed but only changing one parameter. So the way it works is that, let's say that my temperature is high, your marginal distribution looks like this and cumulative distribution looks like that. So that means if you draw a random number, it can fall anywhere, okay? Now, at an intermediate temperature, you can have the probability function looking like this, and the cumulative function looks like that. So, you can either pick somewhere in here or here. On the other hand, at a very low temperature, it might look like this. So my cumulative function looks like that. So if you draw a random number, doesn't matter what comes out, you're always going to pick the one from high probability region. Okay? And you do this for every parameter. Okay? And this is also a pretty robust method. Yeah. As long as you can compute the value of the function. Okay, so what I like the most is this very fast simulated annealing method, okay? Because it's basically a very good improvement on the simulated annealing method. So why is it, what is good about this? So I told you that I go from some model M naught or M prior to M star, right? And here I use some kind of proposal distribution, okay? This gentleman Ingbar, who actually proposed this algorithm, he came up with a very nice idea. He said that why should my proposal distribution be the same all the time? Why can't we actually have a temperature-like parameter in the proposal distribution also? So what it means is that at the search itself, you don't allow, you allow for a lot of faraway models at the initial iterations, but as you go to larger iterations, then you look at the close neighborhood of the current solution. Okay? So here is the probability distribution, which is actually Cauchy-like distribution, which is another parameter for temperature. Now this temperature is different from the acceptance temperature. This is for model generation. So in this figure, I'm showing you how this proposal distribution changes. So you can see if this is your current model. At a high temperature, you can go very far from the current model at the generation itself. But as you go to higher and higher iteration, your distribution becomes narrower, so you don't go very far. But this also has an acceptance probability. Okay? Same as metropolis. So VFSA is a very, very good approach. And one of my students once commented, VFSA is cool. You guys use this word cool all the time. So yeah, you cool it fast. It just worked really well. Okay? So this is the algorithm, if anybody wants to code it. Okay. So now I'm going to switch gear and very briefly talk about genetic algorithms. Okay? So this is a very basic genetic algorithm, and nowadays you have more powerful population-based methods like PSO and few others. But genetic algorithm became quite popular in the 90s and in 2000, early 2000, late 90s, early 2000. And the idea came from, for example, simulated annealing, the ideas came from statistical physics. Genetic algorithm, the ideas came from natural genetics, from genetics, okay? So this is analogous to natural selection process. And there is something that you may have heard, there's a sentence called survival of the fittest, right? Survival of the fittest. What that means is that I say that I have one job opening, okay? And you all are interviewing for that position, right? So then you all work very, very hard to impress me if I'm the interviewer, right? And the one who does the best survives, okay? So then, how do I measure who is the best, right? And that's our objective function. So rather than finding the minimum here, I'm trying to find the maximum, okay? So in natural genetic process, what you have is this concept of gene, okay? And then you have this concept of chromosomes, okay? So you have a whole bunch of chromosomes, and they cross over, they mutate, and then they go through different iterations, and in that process, the fittest one survives. And the way it works in the algorithm is first you define a fitness function, which is your objective function. And what are chromosomes? These are binary coded models. This could be real number coding also, but basic was binary coding. So I'll show you what is binary coding, what is selection, what is crossover, what is mutation, okay? Okay, so let's say that I have velocities that range from 1500 to 1810. Okay? And then I want to describe those with an increment of, say, 10 meters per second. If you do the calculation, you'll see that I need 5 bits. So what that means is that when all bits are 0, this is 1500, and only the lowest order bit is on, it's 1510. When this one is on, this is 1520. And if both of these are on, this is 1530. And so on. And when all bits are on, this is 1810. Okay? So let's say that I have a layer whose resistivity can be between, say, 200 and 300, right? So then we discretize it with 10, and that tells me how many values we have. You have to decide how many parameters, how many bits you need to represent that. Okay? Now I have a whole bunch of these layers with different velocities, right? And each layer can be represented by, say, at least 5 bits. And then we concatenate them in a long vector. Okay? And that is going to be your chromosome. Okay? So what do we do with that? So we can start at random by flipping, with a random choice of these bit locations. That gives me one particular velocity. So I have it for multiple layers. So we start with a population of models. Unlike the method that we talked about so far, where we always started with one particular model. Here, let's say that I start with 100 models or 100 chromosomes. The models are coded, right? And for each one of those models, I can calculate my fitness value, right? If I can compute my fitness value, then I can actually define a probability, and you can do a bias selection. That is the selection process with fitness proportionate selection. So what this does is it basically is biased towards selecting good models. Okay? So from, say, 100 models that you started with, you have 100 new models. Okay? But then you just cannot continue to repeat this because then you're not getting any new model. So what is done here is called crossover. And the crossover is done between pairs of chromosomes. So this is one model, one chromosome, this is another chromosome. And in crossover, you first have to pick a crossover point at random. And to the right of that, you simply exchange the bit. If this is 0, this is 1, this becomes 1, that becomes 0. So in that process, with 100 models that you started with, after selection, you have bias selection. Hopefully, you have better models. But now you have perturbed these models. This is nothing but perturbation, right? So you have another 50 pairs. Then we do another thing, it's called mutation. And mutation is done with a very low probability, where occasionally you change one bit somewhere. Now this actually introduces diversity. This may harm or this may help. Okay, sometimes, I don't know if this is, anyway, I'm not to say this. But anyway, so you have heard about the mutated children or something like that, very smart or very dumb. And that people say is because of this. Typically, the way geneticists actually explain this is that when you have two smart people, generally they expect you to have smart children, right? So in any case, this mutation basically goes through another perturbation of the model. And then once you have these 3 steps, you go through again selection and then crossover and mutation. a large number of times, and then when it converges, means that the population does not have any diversity, okay? And that's where you stop. So this was the mutation. So to summarize, we talked about many different methods, and you can think of these methods as model exploration or model exploitation. So methods such as steepest descent, gradient, Newtons and other things can be called model exploitation. And uniform search is a truly exploration of the entire model space. And simulated annealing, genetic algorithm, these are sort of in between being completely model exploration and exploitation. So more exploration than exploitation. So this is the summary of all the methods that we have talked about. There are other methods, and but typically gradient descent or Newton method in case of local optimization, and simulated annealing for global optimization is the most popular. Okay. So this is where I can stop, and if you have any question, you can ask me. But I think it's time for the next talk. Or we can have a discussion again on this in my next talk. Any question quickly?
Yes, the genetic algorithm can be slow.
Sometimes. And that's why you have now much newer methods where the convergence is faster. And in our application, we actually combine simulated annealing with genetic algorithm also. Okay, then. Yeah, thank you. And I'll see you guys tomorrow because I don't have any lecture this afternoon. Oh, I might see you at lunch. Yeah. Okay. Well, the only thing you can do is cleaning and test. Yeah, so normally you need basically look at the direct way and then integrate and use that, and then later on allow for the application itself, allow for small changes.